Hello, good evening. Yeah, you can hear me, right? Okay, fine. Let's start on today's lecture. All right. So today is introduction to renewable energy, and yeah. So these are the contents for today's lecture. First is the discussion of answers to the questions from last week. Okay. Then we have a recap on the final energy consumption, which we've already seen. Installed capacity and electricity generation in India, the current scenario. Then we have the need for renewable energy, the IPCC report. We'll just have a recap. Then we'll have a look at the solar PV, that is photovoltaic and thermal applications, and then wind power. Some concepts and definitions related to energy and power, and then we have the questions for this week. All right. So, let's go into the questions from last week. The first question was vehicle exhaust accounts for about two-thirds of the life cycle greenhouse gas emission of fossil fuel vehicles. If fossil fuels are replaced with biofuels, how will it aid in enhancing environmental sustainability? There were four options given. I think there was some confusion regarding this. Please understand that whether biofuels emit lower CO2 than fossil fuels to produce the same energy is not known. There is not enough data available. Um, the tailpipe emissions, for example, if you see hydrogen does not emit any carbon dioxide. Okay, if you burn hydrogen, you're getting only water vapor. Okay, so when it comes to hydrogen, obviously this is true, but this cannot be said for other biofuels like ethanol or methanol. So you need additional data for that. All right. Uh, then even when you consider the manufacturing of biofuel vehicles as compared to fossil fuel vehicles, you don't have enough data whether it is more or less. You don't know anything. Okay, but what you do know is that the CO2 emitted from the exhaust of biofuels is carbon neutral, that we've already seen, right? So it doesn't contribute to any new CO2 addition. Okay, and that is the only way as of now that we can just one second. Yeah, that is the only way we can enhance environmental sustainability as of now. I hope you are able to see the screen. Can you confirm? Yeah. Okay, perfect. All right. So the answer is that it's carbon neutral, and hence it contributes to the environmental sustainability. Another point I'd like to mention here, there is something called flex fuel vehicles. That is when you have ethanol or methanol and you want to burn it directly in a vehicle, right? Okay, so you use something called flex fuel vehicles. There is an electronic component that kind of senses what is the fuel. You can use either pure petrol or pure ethanol in that vehicle, in that engine. Okay, so it's not less or more. In fact, it is the same vehicle. It's just a couple of parts that are different. That's all. Okay, so you cannot confirm that the carbon dioxide emitted to manufacture these vehicles is lower or higher. Okay, so the second question was, which of the following statements are true? Your options were levelized cost is an equalized cash flow for equal time periods, which is of course a true statement, because you have unequal cash flows each year, and then you levelize that or equalize that for for better comparison. Basically, it's a standardized measure basically. Second option was money receivable a year later is worth more than the same amount of money at hand today. If you remember time value of money, if you have 100 rupees at hand today, you will invest it, you will get some interest, all right, or you will get some return on your investment. So next year you will have, let's say, 105 rupees in your hand. But if the same amount of money is receivable next year, that is, instead of having 105 rupees next year, you will have only 100 rupees. So you are at a loss of 5 rupees. So the statement is not true. Okay. So money at hand today is worth more than money receivable 1 year later. Okay. The third is economy of scale. So basically, if you go to higher capacities or higher volumes, you will be having lower unit costs. Okay, so this statement is also not true. So the correct answer is A. So the next next question: which of the following statements are true? The first is methane and nitrous oxide are more potent greenhouse gases than carbon dioxide, which is true because methane is about 25 times and nitrous oxide is about 298 times more potent greenhouse gases than carbon dioxide. All right. The second statement was NOx, that is nitrogen oxides and ammonia emissions cause acidification of soil and water bodies, which is also true. The acidification is measured in kg of sulfur dioxide equivalent, but NOx and NH3 emissions also cause acidification. Okay. Eutrophication is caused due to runoff of excessive fertilizers. So and because of that there is excessive nutrient and there is algae growth in all of these water bodies. Okay, so that is what is eutrophication. So all of these three statements are true. All right. Number 4 was which of the following are techno-economic indicators. So as the name suggests, the term techno-economic denotes technical and economic parameters. So you have all of these three, like annual yield, annual availability of feedstock, levelized cost. All these three are techno-economic indicators. All right. So these two are technical and the third is economic. So that's how it is. Number 5 was which among the below pairs of indicators are not conflicting objectives. Okay. So what are conflicting objectives? So when two objectives are contrary to each other. Okay. That is when achieving one goal might affect another goal. So if you think from that perspective, if you want to reduce the biofuel cost, then you have to pay as less as possible to procure the biomass. Okay, but if you do that, then the farmers' income is taking a hit, right? The more you pay to them, the more their income is. So this is a conflicting objective. You want to reduce the cost, but you want to increase the farmers' income. So this is a conflicting objective. The next one is plant capacity versus transportation cost. So you have plant capacity. You remember economies of scale. So if you go to higher capacities, your cost will be lower. Okay, but when you go to higher capacities, you need more feedstock, more biomass. So you have to go your radius of procurement should be even more. So instead of 50 kilometers, let's say you have to go to 100 kilometers. So that is obviously going to increase your transportation costs. So that is also a conflicting objective. And the first generation feedstock for ethanol production, that is you have crops, you have grains, rice and so on. So if you use rice for ethanol production instead of hunger eradication, so obviously you will have lower grain availability for hunger eradication, right? So that is also a conflicting objective. But when you talk about plant efficiency versus biofuel cost, so plant efficiency, if it increases, that means that you are producing more biofuel for lesser input. Okay, that means your biofuel cost will obviously reduce. Okay, so this is not a conflicting objective. So which of the following statements are true? So the first was about particle density. So what is particle density? You take among your whichever solid you have, you take one particle and measure its dimensions, that is for the volume, and then you measure its weight. So the ratio of mass to volume of that particle will give you the particle density. Okay, but you don't do it for only one particle, you take many particles and then take an average of that. So that's why it says here mean ratio. All right. The next is the ratio of mass of large quantity to large quantities to the volume of this quantity, right? So you take a bulk of this quantity and then you put it in a big container and you measure the mass and you know the volume of this container. So that is the bulk density, okay, that mass upon that volume. So, and what is void space? So when you take a bulk of this substance, right, this solid, and then you dump it in some container, it's not going to occupy every single space that is available in the solid is not going to occupy every small space that is available in the container, right? So between particles there will be void space, that is air will be occupying that space, right? So that is called void space. Okay, so as that increases, that means that you have lesser mass, okay, lesser mass for the same volume. Okay, that means that it has lower bulk density. So all of these three statements are true. Okay. Question 7 was the numerical of the economy of scale. So the formula was given to you, right? And C1 is 18.9 million. Okay, V1 and V2 are given already, 26.3 and 100 megawatt. So you just have to apply in the formula and find C2. So C2 is 48 million. Okay, but the unit cost is this divided by 100. So you need it in $1,000,000 per megawatt. Okay, so you got it in $1,000,000. So divided by the output, that is 100 megawatt. So you'll get it in $1,000,000 per megawatt. So this is the answer, 0.48. Next was the global warming potential. Okay, this is very straightforward actually. So you have carbon dioxide in kg and methane and nitrous oxide in grams. Okay, so you have to convert these into kg. Okay, so 11.87 gram is 11.87 divided by 1000, that much kg. Similarly for nitrous oxide. Now it is given that where is it? Yeah, 25 times and 298 times. Okay, so you just have to multiply that. So CO2 plus 25 times CH4 and 298 times of NO2, N2O. Sorry. So that is 9. That if you calculate that, you will get 9.55 kg of CO2 equivalent. Okay. The next about bulk density. Okay, this seems a little complicated, but it's actually very simple. So you have been given that everything is constant, D, Fc, Cf, Wd and Ts, everything is constant. Okay, so you substitute some x. Okay, so you just take this entire thing and then you substitute x. So you have C equals x by Tc. Okay, now what is Tc? Tc is the weight that the vehicle is carrying, right? The weight of your biomass. So how will you calculate the weight of biomass? You know the bulk density multiplied by the volumetric capacity of the vehicle. So you know the truck, how much volume the truck is having, that you know already. Okay, and you know the bulk density you have been given in the problem. Okay, now so if you substitute that, you will get x divided by rho into volume, right? So but the volume is also given as equal, okay, vehicles of equal volumetric density. So that means that this x divided by volume, that is also a constant. You substitute some y over there, okay. So you'll get c equals some y, some constant, divided by the bulk density, okay. So what you've been asked is the ratio of the transportation cost. So C1 by C2, the y is constant, remember, so y will get cancelled, okay, and c is inversely proportional to the bulk density. So C1 by C2 equals rho 2 upon rho 1. So rho 2 you know already 700, rho 1 is 90. You just substitute that, you will get 7.78. That's the answer, okay. So now the activity, before I go to that, let me ask you, do you have anything to ask or any doubts in these questions? I hope you understood the numericals that I just solved, right? Any questions? Otherwise I'll just move on to the activity, and then fine, perfect, I'll just move on to the activity. All right, did anyone try to solve the activity? It wasn't mandatory, of course. I just wanted to know if anyone tried it. It's okay if you have not tried it. I'll just discuss that right now, okay. Yeah, so this was the activity, right? So we are given this equation, okay. The biomass, it is getting combusted to produce hydrogen, water and carbon dioxide, okay. So how many moles of oxygen are required to combust 1 mole of biomass completely, okay, that is the question. And the hint that I had given is you have to balance this equation. How do you do that? You have to look for each atom individually. There are 3 atoms. You have carbon, you have hydrogen, and you have oxygen, okay. In the entire equation you have only these 3 atoms. So each one you take separately, and then you balance them individually from left hand side to right hand side, and then you will. So how do you do that? So I hope you are able to see this. So this is the equation. The first is carbon balance, okay. So number of carbon balance, number of carbon atoms on the left hand side is 1. You have only 1 carbon atom. On the right hand side you have B carbon atoms, okay. B is some unknown. So from these two equations you get B equals 1, okay. You got the first answer. Similarly you do for hydrogen. On the left hand side you have 1.4 hydrogen atoms, and on the right hand side you have 2 into A, okay. You have H2 here, so there are 2 atoms multiplied by A, so 2A. So equate both, you get 2A equals 1.4 or A equals 0.7, okay. Similarly you do for oxygen. So on the left hand side you have 0.6 here and 2x here, 2 into x, okay. On the right hand side you have A plus 2b, okay. So if you equate them, then you'll get an equation. You already have A and B, you substitute the values from above, okay. So once you do that, you will get x equal to 1.05. so you need 1.05 moles of oxygen to completely oxidize 1 mole of the given biomass, and this is the final equation, okay. So CH1 1.4 O.6 plus 1.05 O2 gives 0.7 H2O plus CO2, Okay, this is the final equation. Okay, and in fact, if you are balancing chemical equations, this can be a general trick that you can follow. Okay, you just see which all atoms are there in the left hand side and right hand side, and then you just write it down as maybe some x, a, b, something like similar to what I have done here, right? And then you can solve for it using some linear equations. That will be very easy. Okay, then of course the molecular weight of biomass. So carbon is 12, hydrogen is 1.4. Okay, sorry, hydrogen is 1 and there are 1.4 atoms of hydrogen, and oxygen is 16 multiplied by 0.6 atoms, so it is total is 23 grams per mole. Okay, this is the answer. Okay, got it? If there is anything any doubt, then I'll wait, otherwise we can proceed to this week's lecture. Anything? Okay, I'll just proceed. All right. Okay, so introduction to renewable energy. Some of you might have already had some lectures on renewable energy, and so we'll just see the current scenario. Okay, the final energy consumption. Okay, this is in 2018 the total final energy consumption amounted to around 600 million tons of oil equivalent. Okay, and out of that, if you see industry and residential together amounted to around 60, more than 60%. Okay, so here there is an opportunity here in industry as well as residential to reduce the energy use. Okay, and most of this is electricity, because in residential complexes and in industrial complexes you use electricity as the final energy, whereas in transport, as you know, you use petrol and diesel and other fossil fuels directly. Okay, and electricity is actually very less in transport. Okay, so the installed capacity as of July 2022, as you can see here, about 50, more than 50% came from coal, like the installed capacity, and around 200 so this is coal plus lignite. This lignite is also coal, right? So it's around 210 gigawatt, which is the installed capacity of coal powered plants. Okay, and if you consider other fossil fuels, right, you can see here gas and diesel. Diesel is very less, but gas is like another 6%, and overall fossil power is about 58.5% as of July 2022, and non-fossil amounted to around 41.5%. Okay, and for solar and wind, so solar is about 14% with around 57 gigawatt. Okay, and wind is around 40 gigawatt in just couple of months back, right? But despite having, if you say this, right, it's 24% from only solar and wind. But if you see this graph, this pie chart over here, the total electricity generation, this is from 2 years ago, total electricity generation is like 80% of it is from coal, whereas from renewable energy it's only 10%. Okay, the installed capacity is 25% just for solar and wind, and even hydro is like 12%. So more than 30% is renewable, right? But the electricity generated, actual electricity that has been generated, is only 10% and 7% for hydro. So overall just 17%. So why do you think this gap is there? So that is attributable to the intermittency of solar and wind. Okay, solar is not available all the time. It's only available between when the sun is shining, right? So maybe between 8 and 4, and at full load it generates only from around 11 to maybe 3 or something like that. So around 4 to 5 hours per day is the actual time that it generates, right? And similarly for wind, when wind is available you can produce power, okay, otherwise you can't. So rest of the time you have to depend on thermal power, right, from coal, diesel and natural gas. Okay, so why do we need renewable energy? So this you have already seen a couple of weeks back. So the representative concentration pathways by the IPCC, they have stated that if we continue in the same um, if we continue with business as usual, then we will be heavily dependent on coal. As you have already seen here, we are already very heavily dependent on coal, and if we continue with this, then what happens is that 69% of the global energy demand could be supplied from fossil fuels, okay, and that will lead to a temperature rise of more than 4 degrees Celsius. Okay, our target is less than 2 degrees Celsius, so we need to go for RCP 2.6, which is dependent on bioenergy and other renewables. Okay, so that's about the recap part. So now let's come to solar photovoltaic. Okay, so there are three different ways you can generate electricity directly from solar photovoltaic. uh, this is based on the systems, right? So there is megawatt scale grid connected photovoltaic. There is kilowatt scale grid connected photovoltaic, that is in rooftop solar that you would have seen in buildings and all that, or there is standalone. So what happens in megawatt scale grid connected? So you have a solar field, a huge solar field, okay, and then you have an inverter, because you have DC that is produced, direct current that is produced from solar, from the solar PV. So you need an inverter to convert it into low voltage alternating current. Okay, then you have a step up transformer, okay, which converts this into high voltage alternating current, and in the transmission line you give it to some transmission line, and at some other location there is a step down transformer to convert it into low voltage uh, again, okay, low voltage alternating current again, and then it comes to your house. Okay, because the load here, it takes like 440 volts, okay, but here the high voltage line will be like 11 kilovolt, like 11,000 volts or 33,000 volts of that range, okay, that cannot be used in our homes. Okay, so the next is kilowatt scale grid connected uh, photovoltaic. So what happens is, when you have photovoltaic on your rooftop, it is already near, so in this case in megawatt scale it is in some remote location, okay, somewhere outside the city, but your load center is in the city, right? So you have to transmit that electricity that you have produced from there to here. Okay, in this case the electricity is produced on your rooftop itself. Okay, so the load center is right there. So all you need is an inverter, and then there is an alternating current panel, like you'll have a box or something that you would have seen in your home, right, your mains. You can connect to that directly from the inverter. Okay, and that goes to load. So in this case what happens, whatever excess power you generate, right, in addition to what you are using at your home, that can be supplied back to the grid, and then the government will pay you money, the discom, whichever. In Karnataka we have bescom, in Tamil Nadu you have TNEB and all that, right? The electricity board, they will pay you money for whatever you have sold to them. Okay, so it's not money as such. So there is something called net metering. Okay, so if you install this net meter, whatever you have taken from the EB and then what you have supplied, they will just minus that, and then they will charge you only for the electricity bill only for that amount, that net amount. Okay, so that is called net metering. Okay, then you have standalone PV, which is not very common. Okay, but it is used in some areas, like you have in agricultural fields, you have solar pumps. Okay, so you have a solar panel, then it supplies directly to a pump. Okay, so you have a solar field, that is solar panel, and then there is an inverter, and the energy stored, the excess energy is stored in a battery bank, and at night or whenever there is less solar radiation, right, from the battery bank it goes back to the inverter as DC and then converted to AC again, and then goes to the load. Okay, so here are some pictures, like this is called a string inverter for rooftop application. So this is a very small inverter. The company, this is called Sungrow. This is one of the inverter manufacturers. Okay, and this is how the rooftop solar plant looks like. Okay, this is an RCC rooftop. RCC means reinforced concrete cement. There is also another type of roof, that is the metal roof, right, metal sheet. So in industries, in factories and all, they'll have all those made of galvanized iron, the sheets. You can install solar on top of that also. So this is made of RCC roof. This is a project that I was involved in. Okay, and so you can see there is some kind of foundation that made. So we do some kind of grouting and anchoring. Okay, and then create an RCC structure around that. Okay, so like this. So this is a foundation, and then on top of that we mount these panels. And this is a ground mounted panel with single axis tracking. So this is the tracking system. Okay, so this this kind of rotates along with the panels. Okay, so normally what happens is, if it is a fixed system, right, this is a tracking system, that is, it tracks the sun from east to west. So the orientation of this is east in the morning, and then it goes, and the evening it is facing the west. Okay, but here it is fixed modules, right? So fixed modules are facing south normally, because we are in the northern hemisphere. The sun traces the path of east, south, west. Okay, it does not go from east to west directly. Anytime you notice the sun, it will be slightly towards the south. Okay, and in the southern hemisphere, like Australia or some countries, it will be the sun will always be towards the north. So there the panels are facing the north normally. Okay, and in case of single axis tracking, you are facing east to west, you are tracking the sun. There is also two axis tracking, but that is not very popular because there are many moving parts, and it's not very robust, so to speak. So now we come to the solar thermal for heating applications. Okay, so you would have seen solar water heaters. Like this is a flat plate collector. Okay, this is evacuated tube. Okay, and what is the difference? So in flat plate collector you have so you have these tubes in which water is there. Okay, and these absorbers, the collector plates, are painted black, because black absorbs the maximum radiation, right? And there is a glazing. So why is this glazing there? Because when the radiation comes in, right, so it should not escape out. You need to maximize, and you need to trap it there as soon as possible, as much as possible. So this is similar to the greenhouse effect. Okay, so when you have glass, and then the radiation comes in, it is trapped over here, and we extract the maximum heat out of it. So that's why there is glazing, and then there is a thermal insulation over here. So what happens is, the inlet is over here in the bottom. See, the cold water comes in here, gets heated up, and by thermosiphon, that is because the water, the heated water, right, the hot water has lower density than cold water. It rises up above without any pump. Okay, you don't need a pump or anything. It rises through this, and then after that it is the hot water is stored here in the water tank. Okay, in evacuated tube collector, what happens is, here you have air, here what happens, you have vacuum. Okay, why do you have this? Because you have air here, there is convection between air and this. So there is something called convective heat transfer between the collector plate and the air. So you lose some of the heat that is available. In this case, because there is no air, there is no convection, there is only radiative heat loss, but that is unavoidable. We can't avoid that. Okay, so this has better efficiency than the flat plate collector. Okay, then you have solar thermal for power applications. Like in this case, what happens is, there is no concentration of the sun or concentration of the solar radiation. So as such, the solar radiation is falling on this plate and then it's heating it up. Whereas for power applications, what happens is, you can see here, if this is clear to you, this is like a parabolic mirror. Okay, so, and as you know, parabola has a focal point where if all the rays will be focused on that point. Okay, so there is a pipe running through its focus. So the sun's rays, when they fall on this mirror, right, from all directions they are focused on to this pipe, and this pipe will have some kind of heat transfer fluid, like some oil or something. After that, they will go to a heat exchanger where you have a steam cycle, okay, and a steam turbine to extract energy out of it, extract electricity, okay, with the help of a generator, and then it goes to load. The speciality of such kind of solar thermal power plant, right? You can store energy in the form of thermal energy. How can you do that? There is something called phase change materials. There are special materials that will hold heat. Okay, so the excess heat that comes from the solar field, right, it goes into this storage, and then when it's in the night time, or if it is cloudy or something, what happens is, from this storage you can run the steam cycle. So it's like you can run this, technically you can run this plant for 24 hours even without the sun. Okay, and there are other receivers also, other concentrators also, like you have flat mirrors here, these are called heliostats. Okay, and there is a big tower over here. Okay, this is called central receiver, or a central tower you can call it. So from all of these mirrors, the sun's rays are like concentrated onto this place where you have all these fluids, and then you will have very high temperature over here. Okay, similarly you have something called Fresnel, linear Fresnel reactors. So you have rows of flat mirrors. Okay, and this is like a bridge on top. So from here it will be reflected onto this, and there is either water or some heat transfer fluid over here. Parabolic dish is like you'd have seen that TV antenna, right? That big, it's very similar to that, and it will focus on one single point. Okay, parabolic trough is like a parabola, but it will focus on a line. Okay, but over here the parabolic dish, it focuses on a single point. Okay, so, and that single point is like so it becomes really hot, and you can extract a lot of energy from this. I'll just show you just how much. So parabolic trough, if you can see number of suns. Okay, so from the sun's rays you can get equivalent of about 80 suns. That is the meaning of this. Okay, the energy equivalent of about 80 suns in that line that I showed you, in that pipe, right? but parabolic dish, you see, you have 1300 suns, okay, on that single point that I showed you over here. So you have the energy equivalent of 1300 suns over here and about 80 suns over here, okay. And similarly for central receiver, like I told you, it's very powerful, okay. So it's also more than 1000 suns, and linear Fresnel, it's not very effective, it's about 60 suns, okay. And if you see the temperatures over here, 540 degrees, this is enough actually to run a steam cycle, okay. Similarly here you can get about 540, and this is not enough for a Rankine cycle, that is a steam cycle, but it is still quite a lot. The temperature is quite a lot. If you compare this with the flat plate collector or something, flat plate may go up to 80 or 90 degrees Celsius, and compare it to this like 540 degrees, obviously you can see the effect of the concentration, right? Okay. Then next is, so yeah, what are the differences between solar PV and thermal? Okay, in photovoltaic, it uses direct and diffused irradiation. So what is direct, what is diffused? So from sun, the rays come in, right? The radiation comes, okay. If there is no obstacle in between, if there is no dust or cloud or something like that, it comes directly and hits the earth's surface, or it hits the solar PV plate, solar PV module. So that is direct irradiation, okay. But if there is some dust in between, or some aerosols or whatever it is, or some clouds or something, it gets scattered, okay. That the sun's rays will get scattered. So but it still will reach the earth's surface, right? So that is called diffused irradiation, okay. So solar PV uses direct or diffused, it can use both. Solar thermal needs only the direct irradiation. So if it is cloudy, no, so this is the main disadvantage with solar thermal. Even though you have seen here, you have the power of 1300 suns, if it is cloudy, then it is going to be very difficult, and that's why you need that thermal energy storage, okay. If it is cloudy for, let's say, 3-4 days, you design it in such a way that it can sustain for 3 or 4 days, okay. But that is going to be costly, because the storage capacity will be very huge, right, in that case. And solar PV converts the visible spectrum, that is the photons, into electricity directly. This one, the thermal converts the infrared wavelength of the solar spectrum to heat directly. Solar PV system will produce DC electricity. In solar thermal, you can produce DC or AC depending on the generator use. You can use DC generator. If you need any DC application, right, you can go for direct current. And solar PV, yeah, energy can be stored in batteries only. You cannot have any thermal energy storage or anything. The electricity, you can convert it into chemical energy in battery and then store it, and then when required, you can use that again, as you have seen in the standalone photovoltaics. But here you can it can be stored in special substances like phase change materials, okay. You can store thermal energy, okay. And yeah, and photovoltaic can only be used for electricity based applications, but thermal can be used for heating or cooling. You have something called solar vapor absorption refrigeration system, okay, where you can use heat to cool down a place. Like you can build a refrigerator out of solar heat. That's what this is. This is a very fascinating concept. In case you're where you can just look this up, okay. And or of course you can go for electricity applications like the concentrated solar power. That, and here the receivers or the modules are mostly flat. Here it can be flat or concentrating depending on the temperature of steam or of your application, right. Then wind power. Okay, so here you have the rotor, right? So what happens is the wind comes here and then it moves this rotor. Okay, and there is a gearbox here to change the uh, to increase the speed basically. Okay, the rpm over here is very low, so you need like more rpm here to run this generator. That's why you need the gearbox here, and then from this generator your electricity is produced. Okay, so this is the high speed shaft basically, and you have yaw control and pitch control and so on. So that is to change the direction of the wind turbine. Okay, so the wind power that is produced is directly proportional to the density, air density, the area of this rotor. So you can see the rotor here, right? The swept area, that is directly proportional to the swept area, and the cube of the wind speed. Okay, so if your wind speed is increasing, the power extractable is increasing by that much cube. Like if you're increasing the wind speed by 2 meter per second, yeah, theoretically you can increase the power by 8 times, right? And cp is the power coefficient, and that depends on wind turbine type and wind speed. Okay, and there is something called Betz law. Okay, what that states is that you have kinetic energy in the wind. The moving wind has kinetic energy. That is what is being converted into electricity, right? You are converting that into mechanical energy and then into electricity. So no more than 59.3% can be converted by any turbine. So that is the Betz law, and this 59.3% is called the Betz limit. All right. Okay. So there are some concepts and definitions. Okay. So you look at the diagram here. So this is power demand over time. Okay. So the minimum power demand. So you can see this. There are some fluctuations, right? So this minimum power demand is called the base load. So what is this base load? So when you are designing a power supply system, you need to design in such a way that minimum at least this much is available at all time. Okay, that is the base load. The peak load is whatever is above this line, this black line. You can see this base load, whatever is above this blue area, right? This is the peak load, and this is the peak capacity, like this is the maximum demand. All right. So what happens is, for base load you need stability. So you can use like coal or any thermal power plant, something like that you can use to cover this demand. Whereas peak load you need flexibility. If suddenly the demand comes down, you should be able to turn down the power output or something. And if suddenly it increases like here, then immediately you should be able to turn up. Okay, so you need flexibility. So you have diesel generators, you have natural gas turbines, all of these come under peak load. Like you can use that to supply for peak load demand. All right, and there is something called firm capacity. Okay, so this is the power capacity above the maximum demand, for which the power supply system must be designed for, considering a security margin. So this is the maximum demand, but you won't design your system for exactly this much, right? You will design in such a way that you will provide, let's say, 25% above this or something like that. So that is the security margin you need to consider. Maybe 25-30% above this you'll. So in case of any contingency or something in emergency, you can provide this much, but you will need only this much. So that is the whole point behind that. So so that is firm capacity. Okay, so this formula, this is fine. This you don't need to. So this here PI is the installed capacity multiplied by capacity credit. I'll just come to that. And this is the margin that you have, like 125% of that multiplied by P max. So you have to design for this much. So your supply capacity should be more than this. All right. Yeah. So what is capacity credit? So you have different sources of generating your power, right? So let's say you have wind. Okay. A wind, let's say you design it for 1 megawatt, or let's say 100 megawatt, but you can't get 100 megawatt every time, right? It depends on the capacity of the wind at that particular location. Okay. So the capacity credit is the minimum amount of power that is available overall. Okay. So you consider some period of time, and then the absolute minimum amount of power that is available from your system, okay, to the maximum power, that is maximum installed capacity. So for wind it's around 8% or something, and for solar it has to be 0, because at night there is no generation at all. It's zero megawatt is generated, right? So if you have 100 megawatt of wind, then the minimum is, let's say, 8 megawatt, then your capacity credit is 8% or something like that. And capacity utilization factor is the ratio of actual electricity generation of a power plant over the year to its theoretical maximum generation capacity. Okay. So it is the actual generation over theoretical maximum, or it can also be defined as the total time under full load divided by the total annual operating hours. All right. So this is something. So we'll come to the questions. I hope everything is okay. Any questions until now? I hope it was understandable, right? These concepts and everything. Okay, I'll just proceed to the questions. Okay. So first is, which of the following statements are true for a megawatt scale grid connected power plant? A. Transformers are required to step up the voltage and step down the voltage to match the transmission and distribution voltages. B. These power plants have batteries for energy storage. This is a megawatt scale grid connected solar power plant. Okay. So these power plants have batteries for energy storage. C. The output of a grid connected solar modules can be connected directly to the grid without using inverter. Or D. None of the above. Do we have answers? Yeah. All right. Next question. So as usual, I'll just discuss this in the next week. Okay. So question 2, what is the advantage of evacuated tube collectors over flat plate collectors? So evacuated tube collectors can handle more water per unit time than flat plate. B. Capacity of hot water tank in heat AC is higher. Okay. C. Due to evacuation, that is, you're creating vacuum, the convection losses are lower in evacuated tube collectors than flat plate collectors. Or D. None of the above. Was that clear? Do we have answers, or do you need to see the question again? Should I read the question again? Okay, I'll just go through it once more, and then So what is the advantage of evacuated tube collectors over flat plate collectors? So first is, can evacuated tube collectors handle more water, or B, the capacity of the hot water tank that you have is higher, or C, due to because you're creating the vacuum, right, because of that the convection losses are less, and so you retain more heat inside the tube, okay, in evacuated tube collectors, or D, none of the above. Okay, so if we don't have answers yet, I'll just move on quickly to the next one. Okay, I'll just move on to the next one. Question 3, which of the following statements are true? A, solar thermal power plants use battery to store energy. B, solar water heating applications require non-concentrating collectors. Okay. C, standalone solar PV systems do not require inverters to convert the electricity from DC to AC, that is. Or D, solar thermal power plants without thermal energy storage cannot be connected to the main grid. So which of these are true? Are you sure? 3, 2, wait, let me go back to 2. Yeah, 2 is okay. Number 3, are you sure? I'll show this to you again. The first option is solar thermal power plants use batteries to store energy. Is that right? You need to think. B is solar water heating applications require non-concentrating collectors. That is, you don't need that parabolic trough with a single point focus or anything. It's only flat. Okay, because your temperature required is less than 100 degrees Celsius. So C is solar PV systems standalone do not require inverters. Okay, what does an inverter do? It converts DC to AC. And what does solar PV system produce? Okay, so you need to think about that. Or D, solar thermal power plants without thermal energy storage cannot be connected to the main grid. Okay, I hope you understood. Do solar thermal power plants use batteries? Batteries are used in solar PV, not in thermal. Alright, so solar thermal power plants use thermal energy storage, like you have phase change materials and special substances that you store heat. Okay, and you use that heat and you convert that back into electricity whenever you need it, at night or some whenever it's cloudy or something. Okay, so I hope this is understood. Okay, I'm discussing this anyway next week, but do we have any changed answers for this? If not, I'll just proceed to the next one. I'll proceed, yeah. Okay. Number 4 is, what is meant by capacity utilization factor? A, ratio of annual full load operating hours to the total number of hours in a year. B, the extent of utilization of spare parts in a plant during operation. C, the loss in energy of a renewable power plant due to inefficiencies in its operations. Or D, all of the above. So what is capacity utilization factor? Do we have answers? Anyone? No answers yet. I hope that it was in the last slide before the questions. If that is not clear, I'll just go through that once more. Okay, sorry. So this is capacity utilization factor. So you have a plant, okay? You have designed a plant, let's say for 1 megawatt, okay? So in one day, that plant should produce 24 megawatt hour, because there are 24 hours in a day. 1 multiplied by 24, so 1 megawatt multiplied by 24 hours is 24 megawatt hours. It must produce that much, but solar cannot produce that much. For instance, okay, it can produce only in the morning, or yeah, so in the afternoon, and right. So it can produce at most like 4 or 5 megawatt hour. Okay, that is, it will operate at full load for only 5 hours, let's say. Okay, so your capacity utilization factor is 5 megawatt hour, which the plant has produced, divided by your theoretical maximum, which is 24 megawatt hour. Okay, you can also say that it is the annual or the number of hours that this operates in full load, divided by the total number of hours. Okay, here I've mentioned annual, but it's okay, you can consider it, let's say, for a day. So I say that the solar operates only 5 hours a day at full load, but there are 24 hours. So 5 divided by 24 is my capacity utilization factor. Okay, so now let's see what this is. Capacity utilization factor, what is the answer? So you have your options: ratio of annual full load operating hours to the total number of hours in a year. B is extent of utilization of spare parts, or C, the loss in energy of a renewable power plant due to inefficiencies, or D, all of the above. Wait. All right. Okay. Next, calculate the capacity utilization factor of a solar power plant of 1 megawatt given its average daily electricity generation is 5 megawatt hour. I just gave you this answer just a couple of minutes ago. So can you calculate this? Do you need the question again? I'll just go to the question again. See, the CUF is, you need to calculate the CUF. Okay, 1 megawatt is the installed capacity, and in one day it is generating 5 megawatt hour. Okay, that means it is operating for 5 full load hours. Okay, so what is the capacity utilization factor? Can someone quickly calculate and let me know? Are you sure? Okay, so how many hours is this operating for, this solar? So 1 megawatt into 5, so it is operating only for 5 hours. All right, how many hours are there in a day? So you need to divide those. Okay, so the answer is, I'll just give you the answer, 5 by 24, that's it. So you calculate that. Did someone get it? Okay, I'll just proceed to the next one. Question 6 is, what is the capacity credit of a solar power plant? Okay, so what is capacity credit? I'll just go back to that because I'm not sure if this was clear. So capacity credit is the ratio of the overall minimum available power from a power plant over the entire year or some time period, okay, to the installed capacity. Okay, so you need to think what is the minimum, what is the absolute minimum power that the solar PV plant will generate. Okay, so you have these four options: 50, 25, 10 or 0. Do we have answers? This one C is for which question? 5. Yeah, that's fine. Now 6th, do we have answers for 6th? The capacity credit of a solar power plant. So you need to think of the absolute minimum power that a solar power plant can generate over the entire year, day, night, whatever. What is the minimum? Huh? Do we have answers yet for the 6th one? Can you tell me what is the absolute minimum that a solar plant, you have installed a solar plant, will it generate power at night? No, right? So what is the absolute minimum? All right. So what is the capacity credit of a solar PV power plant? Okay. So what is capacity credit? It is the ratio of the absolute minimum power that a plant can generate divided by the total installed capacity. Let's say you are installing 1 megawatt solar. Okay. Can it generate, or what is the minimum that this plant can generate? Okay. So obviously it cannot generate at night, so that is the hint that I am giving you. Are you sure? Again, absolute minimum, think of the absolute minimum. Can solar generate at night? Yes, absolutely. So capacity credit is 0 for solar, because after 5 o'clock, after 6 o'clock, for the next 12 hours it doesn't generate anything. Okay, so the capacity credit is 0 for solar. All right. Next, identify the true statements. A is power generated from wind is directly proportional to the rotor area. B, higher wind speeds will help generate more power. C, the maximum fraction of kinetic energy of wind that can be extracted by wind turbines is called the Betz limit. Or D, all of the above. Is it clear? Yes, absolutely. All of these statements are true. Okay, so you have it is directly proportional to the area. The higher the wind speed, the more power you can generate. And then you have the Betz limit, which is 59.3% of the total kinetic energy that can be extracted by any turbine. Okay. Number 8 is, it's a conceptual question. Now you have you have a city, and you have to design a power supply system for this city, and you have options. You have solar thermal with storage, you have coal, diesel and natural gas. Okay, so how will you design this? So remember that base load should have stability. Okay, so solar thermal, coal and all that, they have stability. Okay, diesel and natural gas, they are flexible. Okay, So this so you just have to play around with that. So you have your options. So base load and peak load. So base load, you have solar thermal and diesel, or peak load coal and natural gas, or base load, are you using diesel, and peak load all of the other three, solar thermal, coal and natural gas. Or base load, you use solar thermal, diesel and natural gas. Peak load, solar thermal. Oh sorry, I forgot to remove this. Yeah. Or D is base load, you have coal and solar thermal, and peak load, diesel and natural gas. Which of this is true? Do we have answers yet? You can think about this. Okay, if you don't have answers right away, that's okay. You can just think about this and then we can discuss this next week. All right. This is the question. All right. So you need to design for the base load and peak load, and always remember, base load needs stability and peak load needs flexibility. Okay, and where you just need to look where your stability and flexibility is. So your solar thermal with storage has stability, it does not have flexibility. Okay, you cannot you cannot increase or decrease the power output immediately. All right. Coal is the same, you need to have some minimum threshold value at which you have to run your coal power plant. But diesel and natural gas, they have flexibility. Immediately you can increase the input to the engine, or increase the input to the power plant, and then you can increase the power output or decrease it. Okay. Right. Right, absolutely. Okay, so I think we're at the end of today's lectures. So in case you have any doubts or something, you can ask me. If you want me to go through some other slides in this, you can ask me. Otherwise we can just disperse for the day. All right, so everything was clear, right? I hope you understood the concepts, or something that you didn't understand, or something that I need to improve in my delivery or something. Perfect. So yeah, thank you so much for joining. All right, and I'll see you all next week at 6 o'clock, and yeah, so have a great weekend. All right.